everyone. Today we're happy to have Netta Engelhardt here from MIT to tell us about algebraic EPR and complexity transfer.
Thank you. Thank you all for coming. Thanks for the invitation to be back at Berkeley. The last time I was here, I think Rafael was here, Yosunori was here, Armin was here, Steve was also here. So it's a little bit of a close contact. But I know Jeff is here, Luke is here, so it's not exactly, some things have been changed. But anyhow, the last visit was supposed to be March 2020 and it didn't happen, so it's nice to be back here in person. And I'm going to tell you about this work with Tom Blue that appeared in November. I know it's not the title that I sent in. The title that I sent in is from a paper that came out last night. But then I found out just a couple days ago that my student Lisa will be visiting in March and she'll be talking about that. So I figured that we should get a chance to see all the Engelhardt works. And so instead I'm going to talk about something else so you can see the other one get wrong. Okay, so let me begin with a little bit of motivation and some expectation. So there's this general expectation in the field that entanglement should build space-time. And you kind of see it said colloquially and thrown around a lot, entanglement builds space-time, space-time is emergent from entanglement. There's quite a lot of work to this effect. And one of the most standard examples that people use as a justification for this general expectation is the thermofield double. Above the Hawking phase transition, you say, okay, you have two CFTs, and they are very heavily entangled with one another, and the dual to that is Schwarzschild ADS. You get this kind of connection in the both, this is connected geometry, by a nice bridge. Whereas if you look at two CFTs that are entangled, but you're below the Hawking phase transition, you have a lot less entanglement, and so these two are two CFTs that the thermal ADS, or two copies of thermal ADS. They're entangled with one another, but not quite enough to quote-unquote build space-time. I'm being intentionally vague right now. We're going to try to make things more precise as part of the purpose of this talk. Now, this vague expectation that space-time is emergent from entanglement is often framed as ER equals EPR. It's kind of a slogan that is given to this. And one of the ways of trying to make it a little bit more concrete is to say that we expect that if you have some holographic CFTs and they're in some state where you have order 1 originating entanglement between the two sides, then you should get some kind of an emergent connection between the two in the gravitational space-time. And sometimes people also say that if you have an order 1 momentum entropy, then you get a quantum wormhole. Personally, I've always objected to this phrasing because that's kind of, you can define a quantum wormhole that way, but that seemed to me to be not quite contentful, because what does that really mean? Oh, it means order 1 momentum entropy. It's a little bit of a, well, okay, it's not the most robust reasoning. But of course, we're most interested in situations where we have an emergent space-time and emergent conductivity, and then this seems to be saying something which is a little bit more non-trivial than just renaming this as that. Okay, so ER equals EPR is often quoted as this kind of cornerstone of our understanding of space-time emergence. The problem is that in the absence of an independent definition of this thing here, quantum wormholes, this is just a slogan. It's not a quantitative statement. It's not something that we can kind of test against various things that we can calculate and see if it's true or not. It's a slogan. Slogans are great, but we would like something quantitative, like to really understand what causes space-time emergence to happen. So here's an attempt at something a little bit more concrete, a little bit more quantitative. So I'm going to call it classic, and I think I sometimes call it classical, ER equals EPR. So this is a way of trying to quantify a little bit better with the statement of entanglement builds space-time. So if you have enough Von-Neumann entropy, and we're really going to mean by that order 1 over G Newton, in the marginals of some bipartite state, so rho R1 and rho R2 are just the marginals of this on R1 and R2. And each one of those marginals has a semi-classical gravitational bulk description. Then you might expect that the bulk dual to the full state is connected between R1 and R2. So that's one way of attempting to make ER equals EPR more quantitative so we can actually test it and see if it's true. Now, as it turns out, if you don't further qualify various statements here and you don't explain what you mean by a quantum wormhole versus a classical wormhole, it turns out that this statement is actually false. And yeah.
I love the statement, just maybe
of course, yeah.
here, but to make sense, even on the previous slide of enough phenomenon entropy, you needed another scale, right? It wasn't just that the phenomenon entropy was large compared to 1.
Yes, absolutely.
It had to be large compared to some n-squared system.
Yes, absolutely.
Something said by the ADS scale. And we could make the ADS like very large, and then it's never enough.
Certainly. So this is why I was sort of intentionally vague here in terms of what I mean by enough. Typically, what people often mean when they say enough is yes, that if you build some kind of a dimensionless number out of G Newton and H bar and the ADS radius, then it should be large enough, not large compared to that.
But I mean, I'm skeptical. Even in ADS, I'm skeptical that you can really make this rigorous, right? Because you could have a lot of matter near the boundary where it doesn't form a black hole and entangle it between two ADS space.
Well,
I mean, you'd have to prevent it from falling in.
You can try that. And one of the things that we're going to show is you can do something analogous to that and really prove that this doesn't work. And so we need to give a concrete example of something roughly like what you say. The main concern with saying that it works without actually having a concrete example is that ADS tends to try to make matter collapse. And so you might say that, well, you can try to put a lot of matter near the asymptotic boundary, but it's going to want to form a black hole later, and then maybe the dominant
Don't we want these statements to make sense outside of asymptotic ADS spacetimes anyway, in which case having to rely on them.
I agree with you, but I'm going to show you it doesn't even make sense in ADS.
Yeah, I believe that. We're good. Okay.
So, I mean, yes, but before we go away from ADS, let's just ask, does this even work in ADS? And as it turns out, it doesn't. So that makes it, I would say, so much worse, or from your perspective, so much better.
More correct.
More correct, which is better. Okay, so in this talk, the first thing I'm going to do is review this counterexample that I just mentioned to the idea that spacetime is emergent from a large amount of a known entropy, order 1 over G when you make that into a dimensionless number, or order x squared. And then, so this is based on older work with my student Osman from a couple of years ago now, a year and a half ago. And this, then I'm going to continue to an actual proposal for what ER equals EPR should really be. And that's more recent work from this past November. And finally, is an application of this algebraic proposal for ER equals EPR, which is this idea of complexity transfer, a factor of complexity changing allegiance from one system to another, being the one very general way of understanding phase transitions between extremal surfaces and non-extremal surfaces. Okay, so I'll begin with this review of the counterexample that I just mentioned. So the way we're going to do this, we're going to take the evaporating black hole that we know and love. We take an ADS black hole, we couple it to a bath, we evaporate it into a reservoir, and we're going to look at this black hole at 2 times, before the page time and after the page time. So before the page time, this blue wedge over here is the entanglement wedge of the lower dimensional CFT. If we're doing this in GT gravity, I'm talking about this one, okay? I'm going to call this capital B. So this B is living on the circle, it's a moment of time slice. So before the page time, the entanglement wedge of the CFT is a complete Cauchy slice of the bulk. Right? This is a non-gravitational region, this is not counted as part of the bulk, so this is a complete Cauchy slice of the bulk. And after the page time, the entanglement wedge of B is this blue region over here, because the island now belongs to the radiation. And we no longer have a complete Cauchy slice of the entire bulk in the entanglement wedge. So this is a very critical distinction between these two systems over here that we're going to use a lot in this talk. Okay, so now what are we going to do? We're going to pick 2 times, one before the page time and one after the page time. And because the page curve goes up and comes back down, we can pick those 2 times that we're known entropy of B at T1, B again is this lower dimensional CFT, is equal to the known entropy of B at T2. So we're going to pick these 2 times around the page time so that their known entropy is exactly identical. And now we can say, okay, in this system over here, the entanglement wedge of B contains a complete Cauchy slice, so it can't actually be connected to anything. It looks connected in this diagram, but it's not connected by some gravitating space-time. This thing lives outside of the asymptotic boundary. Whereas after the page time, the entanglement wedge of B is connected to the entanglement wedge of R in a classical way. So already we've seen something funny here, which is that the Bernoulli entropy at T1 and at T2 is the same, but it appears to be that at T1, the entanglement wedge of B is not connected gravitationally to the entanglement wedge of R, but after the page time, they are connected. Now, you might say at this point, well, I've always been a little bit uncomfortable with this coupling to a non-gravitational path. Maybe there's something to do with me that you did that. Can you make this example crisper and more precise without invoking this auxiliary system? And the answer is sure. Yeah.
This representative of what you mean by canard.
Sorry?
B is the path.
B is the bulk. B is the low-dimensional CFT, R is the radiation.
I would have thought that you would ask about the entanglement wedge of, let's say, in the CFT versus the external reservoir or something.
Yeah, so the entanglement wedge of the reservoir is the empty set here, if you're just looking at the gravitating system. I think it's going to be a lot complicated, and so it can't be connected to the entanglement wedge of B, which is a complete Cauchy slice and therefore inextendable in the gravitational system.
Okay.
I'm going to make this much crisper in another example we can build from this. So we can sharpen this by considering,
Was that the consensus that just the amount of entanglement entropy was the criterion of?
So you can see quite a lot of papers before this literally say that. And there's even one paper by Sonner and Jensen who claim to prove it. And I think now, in retrospect, a lot of people, including some people here, would say we never believed it. But, I think that regardless of whether you believed it before or after, I hope that by the end of this counterexample, you won't believe it anymore.
I want to say, I don't know whether we ever believed it, but I certainly never believed it.
Just to make sure, by B you mean the entanglement wedge of the boundary or the CFT?
Yes, the low-dimensional theory.
Yeah.
Yeah, so let's get rid of the bath and make this a lot sharper. So the way we can do this is using the canonical purification. So the canonical purification is a procedure that allows you to build a purification of your system, and sometimes without including any arbitrary degrees of freedom. So you take some density matrix, you write it in the annual basis. This is non-holographic, this is a standard procedure we can do in quantum field theory. Then you double the Hilbert space, and you define this pure state here, which you essentially get by flipping the Brostacats, and you take the square root of the eigenvalues. And if you trace out the new degrees of freedom you've introduced by doubling the Hilbert space, then you get your old state back. We're all familiar with this in a particular context. We're all familiar with this in a very particular context with the Gibbs ensemble. We do this procedure to the Gibbs ensemble, we get the thermal field double. And in fact, it turns out that we know exactly what the gravitational dual of this construction is. So, as I just said, you take the Gibbs state, and you double the Hilbert space, you do the canonical purification, you get the thermal field double, which is dual to Schwarzschild ADS. So you have one side of it, and then you double, and you sort of get both sides. So what I mentioned before is that we have the gravitational dual of the canonical purification. And this was done classically by me and Aaron, and was generalized to include quantum corrections by Raphael, Ben, and Marvin. So roughly speaking, the way you do this is you take some CFT and some mixed state rho. This is the entanglement wedge. We assume there's some semi-classical dual. So this is the entanglement wedge here of rho. And if you want to get the square root of rho, the canonical purification of rho, effectively what you do is you double, you CPT conjugate the entanglement wedge, and you glue it across the quantum extremal surface. Classically, you don't have to introduce any extra matter when you do this. Sometimes, most times when you do the quantum case, you end up incurring some shock waves. But essentially when you this construction here, you evolve it backwards and forwards in time, you generate a new two-sided space-time, which is dual to the canonical purification of your original state, which was a mixed state on one bound.
What about if the state, just simply prepare the state where temperature depends on low energy species or something? What do you think of?
It depends on, sorry?
Low energy species or something.
Well, we're assuming this is a semi-classical state. This is a state with a bulk description which is semi-classical. So you could, I'm not sure what the number of species
it's in the boundary, yeah. Some stupid, because amount of entropy makes it still the same. But you still just simply screw up.
Yeah, as long as everything is sort of low energy.
Yeah, but what I was asking is what people are thinking about those things. Like obvious example that.
An obvious example is just the thermal field double. You get the Schwarzschild ADS. You get Schwarzschild ADS by doing this on one side.
Yeah, in that case it's fine. But why people could not believe that amount of entanglement entropy is just sufficient?
Oh, you're talking about the other.
Yeah. It's just confusing. Yeah, confusing.
No, I'm not going to justify a wrong conjecture.
Yeah. Good enough.
Yeah, sorry.
Okay, yeah, but, yeah.
Okay, so now we're going to take this counterexample I mentioned earlier, we're going to make it a lot sharper because we're going to get rid of that. So we take the system B, which is not the bath, which is the lower dimensional CFT. So this is our system, the entanglement wedge of the lower CFT, the entanglement wedge of the radiation. We're going to trace out the radiation. That just leaves us with this. And we're going to decouple the two. So now we have reflecting boundary conditions here, and that also incurs for us a shock wave. And then we're going to canonically purify. So when we canonically purify this thing, what we do is we CPT conjugate it, and that really just generates a second copy for us because these are not connected. This is a complete, maximally extended Cauchy slice. There's nowhere we can glue something to it. And the QES, development QES, is the empty set. So when you CPT conjugate, you just get another copy. Maybe I should have drawn this upside down, but you get the idea. So we get two copies, and they are not connected. Classically, there's no path that goes between them. And so this is not a connected geometry. Now, if we do this after the page time, we trace out the bath, we decouple the two, this is the entanglement wedge, then we're just going to canonically purify. That means we CPT conjugate this, and we generate something that looks kind of similar to the thermofield double. This is connected, single connected geometry. And so what we have are two semi-classical holographic spacetimes. We have the two disconnected ones, canonical purification before the page time. We have the single connected one, the canonical purification after the page time. They both have two boundaries. They both have the same von Neumann entropy. They're both semi-classical. One is connected and the other is not. So I say it's a pretty sharp counterexample to this idea that entanglement builds spacetime. So entanglement does not always build spacetime. And what we'd like to understand now, if we're going to understand what does build spacetime, is what is the relevant difference between these two states, the one before the page time and the one after the page time, that allows us to have connectivity in the canonical purification in one case and does not permit it in the other case. So this is the primary question we're going to try to answer. Yeah.
Maybe you see it better. So is the point that it doesn't always build spacetime? You mean it's not always sufficient, but is it always necessary?
I suspect it's always necessary, yes.
Okay.
But at least in ADS it's always necessary. I don't have a proof of that, but I suspect that's the case. Yeah.
Isn't that just RT in ADS?
Well, but RT, well, we have these pesky examples where, we have cases that don't satisfy even QES by Akers and Pennington. So, who knows how those will work out. So.
You could have tiny black holes that are connected to each other, like classical, but
Well, what do you mean by tiny?
as in,
Small
when you say
compared to
it's necessary, you mean order n squared is necessary?
Well, okay, we're getting to the second part of the talk, which is how do we even define connectivity and what do we mean by classically connected? So maybe we'll hold off this discussion until I get to that. Jeff, you have a question?
Why do we need to think about the pre-page time state at all? Why not just have a post-page time black hole where it has some interior that looks like it's been evaporating for a long time, but that interior is then purified by the interior of another black hole? It's not canonical purification anymore, but it's like...
Yeah, you can do that. The reason that I chose to do this is because I got a lot of pushback from people saying that things like that, oh, you don't know if that's dominant in the path of the goal or whatever. And so here I can say this has to dominate the path of the goal when you build like your replica wormholes computing your the entropy of the radiation.
Okay.
So I would say this is just a little bit more sharp in the sense that you can't get rid of it without getting rid of the big square calculation. Yeah. Okay, so the goal is to sharpen EPR equals EPR so that we can first give a mathematically precise definition of classical connectivity and a diagnostic of what that means in the dual CFT. We want to give a mathematically precise definition of quantum connectivity and what that means in the CFT. And we also would like to understand what is it that happens at the page time that dramatically changes the connectivity properties of the entanglement wedge of the black hole to its purification. So we're going to try to get through all three of those in today's talk. Alright, so that checks off the first bit. And now we're going to go ahead and start talking about this Algebraic proposal for ER equals EPR. Okay, so I'm going to begin with a little bit of intuition. I'm going to begin by saying if we're going to talk about classical connectivity, we should only talk about it in the context of classical spacetimes. So spacetime to be classically connected, it needs to be classical itself. So intuitively, what we mean when we say spacetime is classical at some time is that it admits a slice where nothing is divergent with g Newton if the g goes to 0 limit. So it's basically well behaved in the classical limit. So more precisely, what we're going to do is we're going to define a classical spacetime as the following. We'll say that a spacetime is classical if there exists a Cauchy slice sigma on which the metric components in some basis order g Newton to the 0. Fluctuations of the metric components are suppressed in positive powers of g Newton. And diffeomorphism invariants such as volumes and areas and so on scale as positive powers and non-negative powers of g Newton. So we don't get divergences when the g goes to 0 limit that depend on g, and we don't get fluctuations that are not suppressed in g Newton. So this is how we're going to define a classical spacetime. And then we're going to talk about classical connectivity in the context of spacetimes that satisfy these requirements.
So isn't this going to rule out a post-page time black hole?
You're giving it away. Hold
But
on.
if you-
We'll talk about it. Yeah, we'll get there. That's not a classical spacetime by this definition. We're going to call it quantum volatile because it has this property to diverge with g Newton. We'll define a notion of connectivity for that. But for a classical spacetime, if we have two asymptotic boundaries, R1 and R2 of a classical spacetime, then we'll say the spacetime is connected if there exists a continuous path from R1 to R2, the two boundaries, where the vacuum subtracted length is finite, and this path lives on this Cauchy slice sigma where the metric components are not fluctuating wildly. So this is basically saying that the spacetime, the classical spacetime is connected if it's pathwise connected, and the length of the path is not divergent when you do vacuum subtraction, once you do vacuum subtraction.
Could you explain a little bit more slowly what you mean by the diffeomorphism and various scaling and choosing some positive power? Maybe illustrating that with a very simple example of a classical.
Sure. So if we're looking at, say, the thermal field double, so there exists a slice over here at intermediate times. Can you see this right now?
Yeah.
At intermediate times, where if you look at the volume of the slice, then and you do vacuum subtraction, so you just subtract off the pure ADS, the things that are comparable to pure ADS, it's finite. In other words, if you compute the volume of this, there are divergences because it goes all the way out to the asymptotic boundary, but those divergences do not scale with negative powers of g. It's not that it's finite at finite n, and then goes to infinity as n goes to infinity.
Am I measuring the volume in some unit in Planck units or?
Well, you're just looking at the volume. You're not measuring it in any units in particular. So it will depend on the ADS radius, for example, and it might be divergent, but it's important for us that it doesn't diverge with g.
Do you have in mind that should I take g to 0? That as I take g to 0,
Yes.
it's finite.
Yeah, we're working in the g goes to 0 limit here because we're talking about classical spacetimes.
I'm just confused what units. You have to give me some units, I think.
I mean, we
Fix
just
the
keep it-
geometry in some units, then keep the geometry fixed for taking g to 0 in those same units.
Very good. Yeah.
So I want to say I now possibly do believe the claim that it's only classically, if it has semi-classical and it has large enough entanglement entropy, then it is classically connected. If
I
this is
think
the
I'm going to
definition.
issue a gag order for Jeff for the rest of the talk, so that I can actually get through it without him giving away the ending.
If I consider something like a classical cosmological solution like EPR, and expanding, universe dominated by capitalism matter, what is what would I do to scale G Newton and hold the solution fixed?
So maybe the best way to think about it is in the context of the evaporating black hole. If you start out with some I don't know, around the scrambling time or before the scrambling time, and you take g goes to infinity, or g goes to 0, then you're just pushing the scrambling time off to infinity. So you're never looking at slices at volumes that are at times that are after the scrambling time.
I want to understand how to make sense of this definition of a classical spacetime. Let me ask this way: is a radiation-dominated universe a classical spacetime?
Yes.
Because I don't know how you would hold the geometry fixed as you dial G Newton. So it's not even clear to me how.
Yeah. So in a cosmology. So you can solve the Einstein equation, sure, with some stress tensor A pi GUT, and you solve the Einstein equation, and then you basically then you say, okay, this is my fixed geometry now, and I'm just allowing quantum fields to propagate on it.
I thought we were going to scale G and ask what
When you
G
fix
is.
the geometry, you're not allowing back reaction. You're effectively setting G to 0.
But then I can ask how that if your morphism invariant scale is at very Newman, that is the geometry from the beginning.
So in
So
this
the reason I chose this example is that if I take G Newton goes to 0, that universe actually becomes bigger and bigger. Let's say it's instead of
yeah, so the
equal to
cosmologies and examples, I think that your example of cosmology is one that is going to fall under a different category of spacetimes that I'll define momentarily, where you're allowed to have some things that will diverge as G goes to 0, and it doesn't mean that your spacetime is extremely ill-behaved or or some quantum mess. It just means it doesn't satisfy this particular definition.
Yeah, I guess maybe I'm thinking, I'm not happy with calling, with this definition for what you would call a classical spacetime.
So I think it's classical in the sense that we should, for classical spacetimes, we should be able to take the G goes to 0 limit in a way that doesn't cause any ambiguities. And you can disagree on whether we like that or not. It sounds like you don't. But
Yeah, I completely don't like that. Yeah.
Okay.
Because I can make a small portion of this radiation-dominated universe by just collapsing radiation into a black hole, and there's no notion that would.
I understand. I think that if you consider applying this definition to asymptotically ADS spacetimes only, you might be a little happy.
No, because I can make black holes out of radiation and I collapse.
You certainly can, and the ones that have volumes that scale with G Newton to 1 over G Newton are going to fall under a different category for us. So we're classifying spacetimes based on certain properties. If you prefer, we can call these classical and the other ones semi-classical.
You can call this like the
Geometric. We can
type-based
call it
spacetime.
geometric.
Call
We
this
can
a
call it-
type-based spacetime, then I'm happy.
All right.
Raphael, are you matching quantum radiation or classical radiation?
Thermal radiation, yeah, so it's quantum. So that the
Okay,
energy density is proportional to h bar.
Okay,
Well,
so,
so then
well, I mean, if you have the energy density scale so that, like, G times the energy density is constant, then you can get a classical spacetime.
Yeah, you can do that, but it's not, that's not the natural family of solutions that would arise in theory. Like if I think about, again, Big Bang cosmology, I can, what I can dial is, the curvature rate is effectively at the Planck time, something like that. But I can't, to hold the, or in other words, the radius of maximum expansion. But to hold that fixed while dialing G Newton, I would have to maybe increase the number of species. I'd have to invent stuff.
Energy density to be clear.
Yeah, I'd have to invent stuff like change the number of species in the theory or something like that to be able to do that.
Okay, we're going to get past the intuition slide and Raphael is like the words that we use. Okay, so now I'm going to define quantum volatile spacetimes, which maybe you won't like that definition, but this is what we're going to call them. So what if our spacetime doesn't actually satisfy this definition of a classical spacetime, but still has some notion of a classical convergent geometry? So, for example, we have spacetimes that come about from their cross-product constructions that Jeff and others have written down. And in that context, you have the classical metric, but you have large fluctuations. And Jeff, you can fight me all you want on this, but you guys have large fluctuations. And
No, we do.
Okay, cool.
There's large fluctuation in time shifts.
Yeah. So, sorry.
I'm confused. Which paper are you referring to as Witten et al.? Who has a name that begins later than W?
So,
Make no excuse.
the important thing for us is that while these fluctuations are in fact suppressed, the parameter which is not scaled to G Newton suppresses a parameter which is already G to the 0. And so we think that those should not be classical spacetimes in the sense that we can't think about sending a path from R1 to R2 in a way that path is obviously continuous and classical and not fluctuating and has finite normalized. Another example is the evaporating black hole at times of order 1 over G Newton. So in this case, the space-time volume behind the horizon diverges and the G goes to 0 limit. This also means that we just can't send a path. If we have a two-sided black hole which is evaporating, we can't send a path from one side to the other, which has finite vacuum subtracted length. So we can't really talk about those spacetimes being classically connected. And so, but maybe there is some notion of connectivity. So we want to give these spacetimes a different class and talk about connectivity for that class. So a quantum volatile spacetime is a spacetime where for any slice sigma on which the metric components are ordered g to the 0, either you have fluctuations, which are suppressed with some parameter, but that parameter is not scaling with g Newton, or you have the diffeomorphism invariance that's scaled with some negative tau of g Newton, or both. So again, either one of those would mean that we can talk about a path from R1 to R2, which is continuous and a classical path and has finite vacuum subtracted length. So this makes it difficult for us, it's impossible for quantum volatile spacetime to talk about classical connectivity, though we might still want to have some notion of connectivity. And these spacetimes over here that come about the cross product, there's a sense in which they should be connected. They look kind of like two-sided black holes in the microcanonical ensemble, but we can't really talk about the classical connectivity for them. So instead we're going to talk about quantum connectivity for those kinds of spacetimes. So quantum volatile spacetimes can be quantum connected, but they cannot be classically connected. And we'll say what we mean by quantum connected. Question? Okay, so just to recap the classification, we have classical spacetimes, these can be classically connected or they can be disconnected. We have quantum volatile spacetimes, these can be quantum connected or disconnected. And then we have sort of everything else, which just doesn't admit any notion of connectivity because it doesn't admit an emergent semi-classical geometry.
When you say quantum connected, does that include like
I haven't defined it. I haven't defined
Okay.
it. Yeah.
Okay.
It's
But just for intuition.
It should be true in the examples of the cross product.
Yeah, that's fine. But there's a classical geometry with some small set of things that fluctuate a lot.
Yes.
And it's the classical geometry. The geometry is connected.
Mm-hmm.
There is also a thing people say about quantum
connected.
connected, where they talk about like Planckian wormholes connecting any belt pairs. We're not talking about
We're
that.
going to give a nice, clean definition of quantum connected, and I'm going to do what it is. Okay. So, all right. So, in order to motivate a definition of quantum connected, I want to first talk a little bit about classical connectivity and how we diagnose that in the dual theory. So, a little bit of intuition. If the spacetime is classically connected, and now we're just talking about classical spacetimes for a moment. So, the entanglement wedges of our two boundaries, R1 and R2, share a common non-trivial edge. That's what it means in a classical case for the spacetime to be connected. And we're just going to forget about the subtleties of the quantum volatile case for just a moment. So how do we translate that intuition into something we can talk about in CT language? Well, if we have this situation where our entanglement wedges share a common edge, then if we look at the Bolt-Fox space of low energy perturbations around the state that we start out with, it should contain states that factorize into a product state on the two entanglement wedges. And it's just a statement about quantum field theory in vacuum or a local vacuum. The way of saying this in the dual theory is that the GNS Hilbert space that you construct from the CFT dual to this state, should fail to factorize around R1 into R1 and R2. Now we can go to the algebraic formulation and say, okay, well, we're not considering cross-product improvements for this. We're just talking about the algebra of operators in a large N limit. So the algebra of operators in a large N limit on WR1 or WR2 should qualitatively look similar to the algebra of operators in Riddler space. Just because if you look at the edge of this entanglement wedge here, it looks kind of like Riddler space. And so this intuition bears out, and we can argue, we can show, actually prove, that in this case, for classical spacetime, the entanglement wedges are connected in the sense of the existence of a path, finite normalized length, if and only if the bulk algebra of operators is type 3 in the large N limit. And we can translate this into a boundary statement using the subalgebra duality, sub-region subalgebra duality. So a classically disconnected spacetime, it should basically fail all of these criteria. So we expect that everything factorizes, or that there exists a state in the Bolt-Fox space that factorizes whenever we have this disconnected spacetime. without causing a lot of back reaction. And so we expect, so we say so it fails all of these, that means there's no common shared edge. We expect that the bulk Fock space does include states that factorize into the two entanglement wedges. And we also expect that the algebra of operators of each one of these entanglement wedges should be type 1. If you were to put a pure state, factorized state on these two, and a trace, this should be a type 1 algebra. Now we can say, all right, so it should be type 3 for classical spacetimes. The algebra of operators of WR1 should be type 3-1 in large limit, and it should be type 1, depending on whether the spacetime is connected or disconnected. And we can translate this into a boundary statement using subalgebra separation duality. The subalgebra of operators acting on the boundary of the GNS Hilbert space that we construct around the state that we start out with is type 3-1 in the connected case, and type 1 in the disconnected case for classical spacetimes.
What?
Yeah.
Can I ask about whether, so that maybe you don't want this to fit into the story, but naively I would have thought that I can ask about connected and disconnected in this classic example of like two regions, intervals.
Oh, I will talk about that.
Right. Because there, I mean, when I sort of cross the phase transition, it seems like nothing very special.
100%. I'll talk about the subregion case, and just as soon as we get the full boundary case out of the way, then I'll talk about the specialization to the boundary subregion case. Yeah.
What boundary subalgebra are you talking about here? Like single trace operators and moduli flows?
So this is the subalgebra that we get. We consider the operators that act on the GNS Hilbert space that we build around the state. So we started with some state, sign or 1 or 2.
Yeah.
And then we build the GNS Hilbert space around that state.
Yeah,
and
but which
operators?
operators
That act on that GNS Hilbert space.
Yeah, but which operators are you using? You need, like single trace will not be enough.
These are operators that survive the larger limit. So this typically tends out, so unless you're taking the limit in a state-dependent way, which I'll talk about when I talk about complexity transfer, but if you're not taking the limit in a state-dependent way, then it's just going to end up being the products, finite products of single trace operators.
But if you only have, if you only have finite products of single trace operators, you're only going to get the causal wedge. You're not going to get
actually, you'll get more than that. You'll get everything up to the Python's lunge. If you want to also get the Python's lunge, you get everything up to the outermost QES.
How are you scaling things?
Well, okay, that's a discussion we should maybe have offline.
Okay.
But if you consider,
I would have said the classic like Lie-Tauser algebra will only get you the causal wedge. I would have said the classic Lie-Tauser algebra would only get you the causal wedge and not all the way up.
So the causal wedge is local operators. So it's single trace. It's not finite products. Once you start allowing yourself to include arbitrary finite products, then you should be able to get more than that.
No. Single trace operators in the causal wedge.
But let me finish. If you take the limit in a way which is state dependent, then more operators survive the larger limit. So in principle, operators that don't survive the larger limit, if you take it in a state independent way, if you now take it in a state dependent way, so I'm taking it. I only require these operators to survive a larger limit when acting on this particular GNS Hilbert space, and you get more.
We should talk about this offline, but yeah.
Okay.
Yeah, keep going.
All right, okay. Sounds good. Okay, so now we want to connect, sorry to use that word. We want to link connectivity of bulk spacetimes to essentially to lack of factorizability. And so as long as there's a basic categorization of bulk, which is either classical or quantum volatile, the spacetime is going to be disconnected if and only if the boundary algebras are type 1. So that's what we're going to, that's sort of our definition of disconnected in both the quantum volatile case and the classical case. We're going to say disconnected equals boundary algebras being type 1. In the strictly classical spacetime, we have local quantum field theory in the bulk. This translates into type 3-1 boundary subalgebra if the bulk is classically connected. And so we say if there's a quantum volatile spacetime, we don't have an independent notion of quantum connectivity, but we're going to define it as follows. We define it using the algebras. We say if the boundary algebras of the two boundaries fail to be type 1, and the spacetime is quantum volatile, then the spacetime is quantum connected. Because it's not disconnected, but it can't be classically connected because it's quantum volatile.
So it's just not make sure I'm not understanding you. You're saying this is a statement about the state. If you take the state and you take a set of operators that doesn't divert when acting on this state in large entity.
Yes.
And then if you think about algebra formed
Yes,
by that.
that's right.
And so in that sense, this is a statement about the state.
Yeah, you can think of it, it's a state-dependent statement. It has to be because it's not all, some states will be disconnected and some states will be connected. Yeah.
Feels like you started off by strongly saying that large amounts of entanglement doesn't mean connected, and now
So actually, Jeff, if I go way back, you'll see I said that that's false without further refinements. That's literally the word that I used.
Okay.
And I'm not providing you with the further refinements that are necessary to make that statement true. You can go back and see the slide if you like. It literally says without further refinements, because I anticipated that question.
But it seems like the refinements are about what connectedness means
Yes,
versus
exactly.
about what.
So, okay, I'm going to go back to that slide.
So for instance, in the paper of Sonner and Jensen, which notion of connectivity did they use?
I mean, they were working purely classically, and their spacetimes are classical by our definition, that they're classically connected, but without the further refinement of quantum versus classical wormholes, the statement is false.
I see, so is there something wrong with the Jensen paper?
Well, there's a lot wrong with the words they say, but not with the equations they write. Yeah. All right. I should have that slide available later. Let's see. Okay, so this is the formal statement that we call algebraic EPR equals EPR. So if we're given some bipartite states, psi R1, R2, with an emergent semi-classical, and by semi-classical I mean either classical or quantum volatile dual, R1 and R2 are classically connected if and only if the entanglement wedge of R1 union R2 is classical and the algebras are technically one. R1 and R2 are quantum connected if the entanglement wedge of R1 union R2 is quantum volatile and the algebras are not type 1. And finally, they are disconnected whenever the algebras are type 1. And here I used if and only if, just because we have an alternative definition of connectivity using pathwise connectedness, and we can prove that it's exactly identical to this definition. Okay, so now I want to spend this little bit of time talking about what happens for the pre-page versus post-page black hole, and then I'll answer Raphael's question about separations. And then we'll get to complexity transfer. Okay, so here we have our evaporating black hole before the page time. Now, if we don't decouple the black hole from the reservoir, we sort of trivially have a type 3-1 algebra in the black hole in this region here, because we just have leaky boundary conditions here. So what we're going to do is, because we're not really interested in what happens over here, we're not interested in the interaction with the radiation, we're going to be interested in the canonical purification. We're going to decouple this like we did before and impose reflective boundary conditions. So here's what we have. We have some Cauchy slice over here. The volume of this scales with 1 over G Newton. So we have a quantum volatile space-time before the page time. And we have a Bonham entropy, which scales as order 1 over G. Now, it's fairly easy to see the algebra here cannot possibly be type 1. You can't put a pure state on this without incurring a large amount of back reaction. So you don't have pure states in Fock space, which means that you don't have, your algebra is not type 1. So it's either going to be type 2 or type 3-1. It almost definitely is going to be type 3-1, the algebra for this slice before the page time. So we know the black hole would be either classically connected or quantum connected to its canonical purification, except it can't be classically connected because this volume scales as order with over 1 over G. Okay,
so if we just measure the number of quanta in each interior part, if we just measure the number of quanta in every interior part of the Hawking mode, I wouldn't have thought that would create any significant back reaction. Because typically you'll get...
So Jeff, you and I wrote a paper once with Arvin, in which
it creates back reaction in the past, but not on that traction slice.
But the back reaction is in the entanglement wedge. And so you don't have... You incur a large back reaction if you're going to disentangle enough of the states and put a pure state on.
But I think you're wanting to be able to disentangle a few of them. I would have said the reason you type 1 is you're considering an algebra where you're acting on finitely many of those quanta at any one time, and you need to act on a divergent
Well, so the problem is,
Like-
again, if you're allowing yourself access to things that scale inversely with 1 over g, then you're allowing yourself to evolve backwards in scrambling time, and then disentangling these is going to cause a large back reaction. I mean, if you want to put a pure state on this, then you're going to have to break a lot of entanglement, an order 1 over g Newton amount of entanglement.
Yeah, I agree.
And that's going to cause a lot of back reaction if you allow yourself to, if you're looking at the entire entanglement range.
I think it won't cause more than breaking an order 1 amount if you look at the entire tangle wedge. So I would have said it's not the back reaction.
Yeah, we decouple, so the entanglement, you're just looking at the wheel of the whip patch here. Right?
Yeah.
You're going to if you want to
But
define.
just measure the red and the blue mode on the right.
Okay.
Right, that's like 2 modes.
Uh-huh.
Now go back in time, or just do anything to them. Now go back at scrambling time, and you'll get big back reaction.
Yes.
And it will, change shape, create white hole singularity and stuff. But that hasn't, it hasn't involved removing an order 1 over g amount of entanglement. It's involved removing like 2 bits of entanglement.
Sure. I
Didn't even really move
I
them,
don't
just
think we're disagreeing with each other here. All I'm saying is that this can't be type 1 because pure states will incur a large back reaction. I'm not saying that non-pure states will definitely not incur large back reaction.
Almost every state will incur a large back reaction.
So, as long as you agree with me that putting pure states is going to dramatically change the entanglement wedge, then I don't think we're disagreeing. Or at least we're not disagreeing on the important things.
So you think the algebra type is type 1?
No. Well, I think to get a good von Neumann algebra, you need to restrict to only acting at finitely many points in this divergent length thing, and then you can't disentangle all the modes because you just can't act on them.
So the spoiler on this is that this algebra is secretly like the algebra if you put quantum fields in flat space and you take the thermodynamic limit.
Yeah, exactly.
That's exactly what it is. That's type 3-1.
Yeah, it's
So
type
that's
3-1
basically what this
because,
algebra
but it
is.
has nothing to do with back reaction in that case, and it doesn't have to be
So
back
you can
reaction.
see this using back reaction, you can see it using a very painful technology that Hong and I had to go through to show that it's equivalent to flat space at the thermodynamic limit. Either way, it's type 3-1.
I agree with that.
Okay, as long as we agree that it's type 3-1, then I think we're fine. There are many different ways of motivating it. You're right that the only concrete way of actually doing it is to map it to the flat space and the thermodynamic limit. Okay, so here we have the p-page versus post-page black hole. So before the page time, we have as this quantum volatile space-time, and the algebra of operators is not type 1, which means that the black hole is quantum connected to its canonical purification. After the page time, these volumes do not scale with order 1 over g, so they don't scale with g Newton at all. And so the space-time is classical, and indeed we get a classical path from here to here with finite and normalized length. And so this is classically connected. So what we have essentially is a situation where the evaporating black hole and its canonical purification, they start out before the scrambling time as being disconnected, then they become quantum connected, and eventually they end up being classically connected. So this is sort of an interesting story of the black hole evaporation process and the page curve, where we go from disconnected to quantum connected to fully, robustly classically connected.
Just a terminology question. Before you go to the canonical purification, do you want to say it's classically connected because the entanglement wedge doesn't diverge, or the full space-time is quantum volatile, or whatever you call it, so it isn't classically connected?
So before we go to the canonical, you mean once
Well, just the post-page time state.
Yes.
Yeah, the post-page time evaporating geometry, would you say that's classically connected, or?
Yes.
No, down.
This one.
That one.
Yeah, so that one, so you can talk about classically connected to what? So you might want to talk about classically connected to the radiation, because at this point we haven't introduced the canonical purification. So you can ask, is it classically connected to the radiation? The annoying thing the thing that is sort of, a very small print over here, is that the radiation is actually quantum volatile here. So what do you really mean by it being classically connected to something which is quantum volatile?
Yeah.
Now, one way we could talk about it is we could say, well, does there exist a unitary transformation you could apply to the radiation, and then have the WB classically connected to that thing? And the answer is yes, of course it is, because that's the canonical purification. So if you want to define it that way, then you say that then yes, this is going to be classically connected to the radiation. Okay, so I guess actually not great on time, so I'm going to skip the time-dependent.
So it's classically connected to the radiation, but the radiation's not classically connected to it. Is that the...
Yeah, that's kind of what
Efficient
it is.
body
Yeah,
line.
that's right. Yeah. So unless there are objections, I'm going to skip time-dependent ER equals EPR because I've kind of been operating under the assumption that I started at 4, and that turned out to not be the case. So it's just a statement that if we want to, we can refine ER equals the algebraic ER equals EPR to change as a function of time, so the spacetime can be classically connected at intermediate times, and then only quantum connected at late times. But I'm going to skip that in the interest of addressing Raphael's question. So, as Raphael astutely pointed out, for some regions it seems that the algebra is type 3-1 no matter what we do. So, here we have R1 and R2, R1 and R2, and the algebra is type 3-1. You can see this due to the fact that this has an edge in the space-time, so locally it looks like Ringler, both in the case when R1 and R2 are connected here, and when they're disconnected over here. So it seems that the proposal fails when we're talking about subregions.
So was that a proposal that connected to something?
Well, they're connected to each other. That was the proposal. That R1 and R2 are connected to each other through the bulk. If the algebra of operators, if the space-time is classical, the algebra of operators of W.
I'm confused. I thought we were looking at one of the systems, we have two, one of the systems.
I was, but now I'm generalizing. So before it was a pure bipartite state, so this situation did not come up. But now we'd like to be able to also talk about multipartite states, so we can talk about the reduced density matrix on R1 union R2, which is no longer a pure state.
Okay, so you're generalizing. Before
Now
you just looked at
generalizing,
one.
generalizations to subregions and multipartite states. Yeah, to answer Raphael's question. Okay, so another example where this fails is if we have just many boundary system. So if we have, say, 4 boundaries, then the algebra, AR1 and AR2, in this case and in this case, are both going to be type 3-1, because in this case, in AR1, it has a boundary, an entanglement which has a boundary in the interior of the spacetime here, and also has a boundary in the interior of the spacetime here. So in both cases, the algebra is going to be type 3-1, even though in this case, R1 and R2 are connected through the bulk, and in this case, they are not. So it appears that we have a problem, at least if we want to generalize. And so instead we come up with a protocol where we basically say we're going to purify, we're going to bipartite the multipartite state. We're going to purify it, and then we're going to redivide it. So we started with some mixed state, psi R1, R2, maybe R1 and R2 are 2 subregions, maybe they're 2 asymptotic boundaries, and we're going to canonically purify it. So now we have psi R1, R2, and then on R1, R2 tilde, which is the second copy that we introduced. So now we have a 4-party pure state, and we're just going to repartition it into R1, R1 tilde, R2, R2 tilde. So we end up with a new bipartite state to which we can apply the old result. And what we can prove is that if AR1, R1 tilde is type 3-1, and again this is for classical spacetimes, it's a similar story for quantum volatile, but I got to the clarity, I'll stick with classical spacetimes. If AR1, R1 tilde is type 3-1, then the entanglement wedge of R1, R1 tilde is classically connected to the entanglement wedge of R2, R2 tilde. So this is just follows directly from our previous result. Now, when is it that the algebra of R1, the algebra AR1, R1 tilde can be type 3-1? Well, so here are 2 examples. So R1 and R2 are disconnected here. AR1, R1 tilde in this case is not type 3-1. In the classical case, it's just going to be type 1. Here, R1 and R2 are connected, and the algebra AR1, R1 tilde is going to, so AR1, the entanglement wedge of R1, R1 tilde will have an interior spacetime boundary, and the algebra of AR1, R1 tilde will be type 3-1. And so effectively what we get is that this algebra of this repartitioning of R1, R2, R1 tilde, R2 tilde, this algebra is type 3-1 only when the entanglement wedge, if the entanglement wedge is classical, only if R1 and R2 are actually classically connected. So now let's talk about some other examples of this phenomenon. So if we have 2 asymptotic boundaries that are connected to one another through the bulk. So what do? We do a canonical, to test if they're connected, we do a canonical purification. We get this geometry. And then we ask, what is the algebra of operators AR1, R1 tilde like? Well, here we say, okay, there's an internal space-time boundary, classical spacetime. So that means the algebra AR1 tilde is type 3-1. And indeed, already the original spacetime R1 was connected to R2. Here we do the same thing. We're going to do a canonical purification on R1, R2. We have this. The algebra operators, AR1, R2, AR1 tilde is type 1. And indeed, in the original spacetime, R1 and R2 were disconnected. And we can just keep on doing this. R1 is connected to some other spacetime, R2 is connected to some other spacetime. We do a canonical purification, AR1, R1 tilde is type 1, and R1 and R2 are not connected to one another in the original spacetime. So basically, we can use AR1, R1 tilde, AR2, R2 tilde to tell the type of algebra to tell whether the entanglement wedge of R1 and R2 was connected in the original spacetime. So this is the proposal for R1 for a mixed state or on many boundaries or on multiple subregions. So given some mixed states, IR1 or 2 with a semi-classical bulk dual, there's emergent classical connectivity. If the entanglement wedge of R1, R2 is classical, and these two are type 3-1. There's emergent quantum connectivity if the entanglement wedge is quantum volatile, and these two are not type 1. And finally, R1 and R2 are disconnected if these two are type 1. So this is a generalization of the,
Based off this protocol for the example of the evaporating black hole after the page time, so what you did before was you did the canonical purification, which you can see if that was connected, but with the protocol you just said, shouldn't you be looking at the canonical purification of both the black hole and the radiation, and then seeing if that was...
So the evaporating black hole is it's a bipartite state. You just have the black hole and the radiation. You don't need this overkill for that situation. You just use the previous protocol where you find that the black hole is classically connected to the radiation after the page time. It's quantum connected to the radiation before the page time, and it's disconnected from the radiation much before the page time. But you don't need this for that because this is just for this is a generalization for mixed states. When the union R1 R2 is still in mixed state. Okay, so spend just a little bit of time. Is that okay on complexity transfer? Okay. No, so we have this precise definition of what we mean by classical connectivity, which is diagnostic in the CFT. We have a definition of what we mean by quantum volatile spacetime and quantum connectivity, and diagnostic in the CFT. We still have to answer one question, which is what is it that happens at the page time that's so different? You could say, oh, your spacetime went from being quantum volatile to being classical, but why did that happen? What is it that shifted in the CFT that really changed before versus after the page time? And so that's what we need to answer with this final point over here. This is this application to complexity transfer. Okay, so what we want to do is we want to identify the relevant subalgebras that we need to talk about before versus after the page time. So in geometric terms, what happens for the evaporating black hole before the page time versus after the page time is fairly obvious. The island changes allegiance from being part of the B system to being part of the R system. So after the page time, the island is part of the radiation. Before the page time, it's part of the black hole. So we also know that reconstruction of the interior, the reconstruction of the island in this case, from the radiation is exponentially complex in the entry of the black hole. The old results were hollow and Hagen. And the holographic realization of this is the strong Python running proposal, and the dual of the non-minimal quantum extremal surface. So we're interested in understanding this phenomenon of the island changing allegiance. So the island is exponentially hard to reconstruct, so we're looking at exponential reconstruction complexity. So just to remind you, the region outside of a non-minimal quantum extremal surface admits a simple reconstruction. So operators that are localized in that region will admit a sub-exponentially complex reconstruction. But the region behind the non-minimal quantum extremal surface is exponentially hard to reconstruct. So what we're interested in is identifying the subalgebra. So this is the outermost quantum extremal surface. For the evaporating black hole, this is going to be the edge of the island. And what we're interested in is identifying these different subalgebras. So there's the algebra operators outside of the outermost quantum extremal surface, and the algebra operators behind the outermost quantum extremal surface. This is the Python such. So I've called these I for interior and O for outside. So in the G goes to zero limit, we have this decomposition. Whenever you have a non-minimal quantum extremal surface, the algebra in the bulk, this Cauchy slice, can be generated by this algebra together with that algebra. Now, what we're interested in are what are these algebras in the boundary theory. So this algebra maps to simple operators. It's the algebra of simple operators. This is not a thing which is an algebra except in the n goes to infinity limit. And this is the algebra of high complexity operators acting on the Janus Hilbert space. So again, these are algebras in the large N set. So that means that we now have a way of identifying the transfer of allegiance of the island from the black hole to the radiation. Because there's this high complexity factor over here, which changes hands. So the page-time is marked by transition of this high complexity type 3-1 algebra, subalgebra, from the boundary theory into the reservoir. So here in this case it belongs to B, and in this case it belongs to R. So this is the crucial shift. We have this type 3-1 algebra that changes hands before versus after the page-time. And in fact, we can apply our connectivity criterion. We can actually talk about, well, is this high complexity factor actually connected to the radiation? Is it connected to the black hole in some way? Given how short I am on time, I'm going to skip this. It's just basically showing that the island is quantum connected to the black hole. So I'll go ahead and skip this. We can actually talk about this transfer of the complex algebra more generally. If you buy the Python's line proposal for subregions, then essentially whenever you have a shift in the minimal quantum extremal surface, that is the result of a high complexity type 3-1 algebra changing hands between either between R1 and R2, or R1 and R2 in the complement of R1 and R2. So we can understand phase transitions of QESs, which you could say have been puzzling. You could say, oh no, we've understood those a while ago, but either way you can understand them in the language of the change in this type 3-1 factor that changes hands from the region to its complement. Okay, so a few comments because my voice is really running out of steam. So we have this algebraic reformulation of ER equals EPR that is the appropriate refinement that is needed to make the classic one correct, and also with some of the definition of what we mean by quantum wormholes and quantum connectivity. We also give a formulation of this proposal for subregions and multipartite states, which allows us to talk about connectivity of those without running into all kinds of funny issues about the type 3-1 algebra. And we identify a way of using this high complexity algebra, which is a type 3-1 algebra that's not associated to a subregion on the boundary. It's associated to a complexity factor, which is unusual. And we can use it to discuss connectivity between the island and the radiation. Again, even though those are not actually geometric subsystems on the boundary. And again, this is also a more general phenomenon that accounts for phase transitions of QESs. All right, thank you for your attention.
So I have a question about can you go back a second to the summary slide of the black hole evaporation?
This one?
No, sorry, the summary of the results of the canonical purification, sorry. Yeah. It was before you started talking about subregions.
Before meaning this one, or?
It's okay. Anyway, what I mean is, I read the one
I'm
before.
going to keep going until you tell me to stop.
It's right before just the summary of the canonical purification before you talked about subregions.
Oh. This?
Yeah, thank you. So on the bottom there, you have a spacetime that I believe that is, by your definition, quantum volatile. Is that right? If you take the last spacetime.
So this spacetime here.
Yeah.
It depends on whether you're talking about WR or WB. If you're talking, so B is classical, but R is quantum volatile.
Okay. So I guess one intuitively would expect that then the connectivity between B and R could always be quantum, but in this case it looks like it's classical. So does this connectivity definition mean that if you have that property of the algebras, then it means that there exists a unitary transformation that gives you a space-time which is classically connected?
So I would not. Yes, that should be true actually. If you have a classical space-time, You have a classical entanglement wedge, and you have and its purification in the spacetime you're working with is quantum volatile, and then you want to say, okay, in what sense are they connected? Then it's true that there always exists a unitary you can apply to the quantum volatile system to turn it into a classical system, which is classically connected to your original, to the classical entanglement wedge. So if you wanted to, and we do actually do this, we define in a situation where you have a classical entanglement wedge and a quantum volatile entanglement wedge, we define them to be classically connected, even one of them is quantum volatile. If there exists a unitary that you can apply to the quantum volatile one, it gives you a classically connected spacetime.
Right, I see.
Yeah. You could have taken a different perspective and said, no, that's quantum volatile, they only ever at most quantum volatile connected, or quantum connected. You could have taken that approach too, kind of agnostic, but, and then in the end we opted to go for the one where if you apply the unitary, you get classical quantum.
Okay, so the point of view is, no matter what the initial spacetime looks like, what matters is only the type of algebra, and if you find that given this property of the algebra is classically connected, it just means that the quantum volatile spacetime is really just a representation of another spacetime.
Sure, but you could also be in a situation where both sides are quantum volatile, and then the best you can do is quantum connected.
Right.
Yes.
This is, I think, it's how the things are happening, say, from Greenland to Minkowski or something. You can apply this quantum, not as a Hawking radiation, but it's kind of horizon degrees of freedom or some crazy thing. If you have a classical thing on one side, then it's always, you can give this the continuation of classical spacetime.
Yeah, I mean, you can also kind of think of it as, well, if this is classical over here, then there exists a path that goes from this a little bit into the other entanglement wedge. And so it's kind of, that's kind of the intuition. If the spacetime can't be fluctuating wildly, just on the other side of this QES, it's completely fixed on the other side. That's kind of the intuition behind this. We can't prove it, but yeah.
Thank you.
Is it like literally then? So like when I was thinking about it, just is that really type 3-1 being enough? I'm pretty sure you need type 3-1 in the large entity. But do we need to have some structure to say actual classical space? Somehow it's like, say, species independence or something, right?
It's certainly not, you cannot tell the spacetime, whether the spacetime is quantum volatile or classical based purely on the type of algebra. So in this case, this is type 3-1, even though it's quantum volatile, and this is type 3-1, even though this is classical. So both of these are type 3-1 algebras. Now, one of the things, future directions we're hoping to look at is more refined aspects of the algebra and various instructions that can actually pinpoint the difference between these two. It's actually kind of surprising that there's no literature on this, just because this is type 3-1 in the regular sense, and this is type 3-1 in the thermodynamic sense. And yet, I don't know of anything in the literature, any quantity in the literature, math literature, on algebraic quantum field theory that can diagnose the difference between a type 3-1 in the thermodynamic limit and a type 3-1 that arises from the window case. I have not found anything. So if there is something, we're going to have to define it ourselves.
They're isomorphic as algebras. They're like they're isomorphic as algebras. Like you can do a conformal transformation to take one to the other.
Yeah, but on the other hand, you have to admit, like, the type 3-1 intuitively is coming it's the type 3-1 for very different reasons. Yeah. So it seems obvious.
It's an IR divergence versus a UV divergence, right?
Yeah,
conformal
exactly.
transformation takes one to the other.
Right? It's just. I mean, I would love to know if you have a hunch as to what can diagnose the difference between them. We have not been able to find it. We've looked a lot.
Yeah, I don't think you can see a difference from the algebra. Like there is only one hyperfinite type 3-1.
Yeah, there's only one type. Exactly, there's only one type. And then the question is, there more refined structure that one can use to distinguish? Because there's no way of distinguishing between the thermodynamic limit and the Windler space that you have got. There's got to be a way to figure it out.
But I mean, if you're in 2D Minkowski free field theory, right, or just any conformal field theory in 2D, you can just do a conformal transformation and one becomes another.
Yeah, but the things transform into a conformal transformation. So you could say, so what are the? I believe that there exists a mapping between the two, but that does not make them identical.
I mean, you could look at algebras on like if there's a UV divergence, it would show up in it will show up in algebras on smaller regions as well. But yeah, anyway.
I mean, I want to pick your brain on this, yeah.
The thing I still want to understand better is exactly when you talked about the GNS Hilbert space in algebras, exactly what algebras you were meaning and.
So we're generating an algebra using the GNS construction.
Like, so with arbitrary single trace ones, anyway, so that gives you some Hilbert space. That's only if your perturbations about the vacuum, then fine, it's the full Hilbert space. But then what's the algebra you're associating subregions?
What's that, sorry?
What algebra are you associating subregions? Like if it's just products and stuff, products and sums of single trace operators.
But it's not though, it's not. Those are the things you get in a, we might have to continue this conversation in a bit. But that's what you get in a state independent, when you take a state independent limit, but you're not focused on any particular GNS Hilbert space. You just, those are, you get those. If you're focused on a particular Hilbert space, then a particular GNS Hilbert space, you're focused on a particular state, then you generate a larger algebra of operators that survives the larger limit. Meaning you don't get divergences in the larger limit. It has to. You should just think about ADS-CFT, right?
Yeah.
We get the set of operators that you get for reconstructing the causal wedge, let's say, is it's the same sort of no matter what space you're talking about. But then you have all the operators that are emergent behind the horizon, which differ from state to state. And so there's a state-dependent limit that you're taking to get those operators to
I'm just interested in what, like from a boundary point of view, when you call them boundary operators, like what you're actually thinking of. Like I think it's probably like modular flows of single trace operators, including any modular time evolution of a single trace operator.
Yes, but this is something that is high complexity. It's high complexity.
It's modular flows high complexity, so it's like.
In general, it won't survive the larger limit unless you're taking it in a state-specific way.
Anyway, we can talk about that.
Okay, so we've had several questions. Maybe let's Netta again. And